In the previous video, we learned about what shear load is and what shear stress is. In this video, we will cover two basic topics in the strength of materials: compression stress, which occurs due to a compression load, and another important topic, strain, which occurs due to the permanent elongation of the material. Let's dive into the topic to understand these topics. Now let us come to our main topic, what is called compression stress. Consider a cylindrical rod that is pushed by force F at both ends, as shown in the figure. Can anyone say what happens to the rod now? As everyone knows, the rod will now tend to deform in the opposite direction of the applied load or force. To resist this deformation, internal resisting forces develop in all the cross-sectional areas of the rod. Hence, the compression stress is defined as the resisting force against the pushing force offered by the unit cross-sectional area. Compression load is a force that pushes a body inward and causes it to shorten along the direction of the applied force. In this simulation, we can see a straight rod subjected to a compressive load. When the applied load is zero, the rod remains in its original shape without any deformation. As the load is gradually increased using the slider, the rod begins to shorten due to the development of internal compressive stress. With further increase in the applied load, the deformation becomes more noticeable, and the rod resists the load by developing internal forces opposite to the compression. This simulation helps us clearly understand how a compression load acts on a rod and how materials respond to compressive forces. Let us consider the free body diagram of rod, which has two push forces at the end. How does this compression load react on the rod? To resist the elongation, the material develops an internal resisting force within its cross-section. But how will this happen? Let us take the cross-sectional area A. First, consider the left side sectional area, where the resisting force is acting on the body opposite to the applied load to resist the material from being away from its stability. Similarly, in the right-hand side, the resisting forces will act in the opposite direction to the applied load. Hence, the body will remain in equilibrium, and no further elongation occurs. But note, this equilibrium will persist only till the elastic limit of the material. Compression stress is defined as the compression resisting force offered by the material per unit cross-sectional area when it is subjected to a compression load. Mathematically, compression stress is equal to the applied force divided by the cross-sectional area. Here, F is the applied compression force, and A is the cross-sectional area. The unit of compression stress in the SI system is Newton per square millimeter, Pascal, or kilogram per pound per square meter. In practical engineering applications, Newton per millimeter square is commonly used. I hope you are clear with the topics covered in the previous video, like tension stress, compression stress, and shear stress. We came to the conclusion of the stress-related topics. Hence, now we will move to the next important topic called strain, which occurs due to the elongation of the material when it is subjected to any type of load. Strain is the deformation produced in a body due to the application of stress, and it is defined as the relative change in length or shape compared to the original dimension. Whenever a load is applied to a structural member, the material either elongates, shortens, or changes its shape, and this change is known as strain. In this example, the rod is subjected to an axial load, causing it to elongate from its original length to a new length. The ratio of this change in length to the original length is called longitudinal strain, and it has no units. Strain is different from stress because stress represents the internal intensity of force acting within the material and cannot be directly observed. Strain, on the other hand, represents the actual physical deformation of the material, which can be seen, measured, or recorded using gauges and instruments. In simple terms, stress is the cause, and strain is the effect that shows how a material responds to the applied load. Strain is defined as the ratio of change in length to the original length of a body, and it is represented by the symbol epsilon. Mathematically, strain is expressed as delta L divided by L, where delta L is the change in length and L is the original length of the member. This definition helps us quantify deformation in a material under load. Based on the nature and direction of deformation, strain is classified into different types. Tensile strain occurs when a material is subjected to a pulling force, causing it to elongate along its longitudinal direction. Compressive strain occurs when a material is subjected to a pushing or compressive force, resulting in a reduction in its original length. Shear strain occurs when tangential forces act on a material, causing layers to slide over each other and producing angular deformation rather than a change in length. Volumetric strain represents the overall change in volume of a body due to deformation occurring simultaneously in all three directions. Strain is said to be a dimensionless quantity because it is the ratio of two lengths, both measured in the same units. Since the units cancel out, strain has no unit or dimension. This means strain represents relative deformation rather than absolute deformation, allowing it to be used universally for comparing material behavior. This example explains strain using a clear visual representation. In the first image, different types of loads are applied to a structural member. When a tensile load is applied, equal and opposite forces act away from each other, causing the member to elongate. When a compressive load is applied, the forces act toward each other, resulting in a reduction in length. In the case of shear loading, parallel forces act in opposite directions, causing one layer of the material to slide relative to another. In the second image, the effect of these applied loads can be clearly observed. The dotted line represents the original length and shape of the member before any load is applied. The shaded portion represents the deformed shape of the member after the load is applied. By comparing the original dotted outline with the deformed shape, we can clearly identify the deformation produced, and this difference represents the strain developed in the material. To conclude, let us quickly summarize the key points discussed in this session. Compression load is a pushing force that acts toward the body and tends to reduce its length. Compression stress is defined as the applied load divided by the cross-sectional area over which the load acts. Due to the application of compression load, deformation occurs in the opposite direction of the applied force. Strain represents the ratio of change in dimension of a body to its original dimension, and it helps us quantify how much deformation has taken place. Since strain is a ratio of two similar quantities, it has no unit and is therefore a dimensionless value. These fundamental concepts of load, stress, and strain form the foundation for understanding the behavior of materials in real engineering structures. Thank you for taking the time to watch this explanation. I hope this session helped you clearly understand the basics of compression, stress, and strain in a simple and visual manner. If you found this content useful, please support the channel by liking the video and sharing it with your classmates, friends, or anyone preparing for engineering studies. Do not forget to subscribe to the channel and enable notifications so you never miss upcoming videos. More easy-to-understand lessons on strength of materials and core engineering concepts are coming soon, so stay connected and keep learning.